One of the most useful ways to evaluate the performance of classification models is to measure the area under the ROC curve. And the ROC curve basically balances sensitivity and specificity. So balancing true negatives, true positives by plotting sensitivity against 1 minus specificity. ROC stands for receiver operating characteristic based on its original use. Here's a link here that explains the origin of that name, but it's not really very meaningful today. And it's a particular way of depicting how well a classification model performs. So as we can see here, you have three different models, A, B, and C, and each model is plotted against how well it predicts true positives here versus how well it predicts true negatives on this side. And the ones that perform better are more concave outwards. That is, they get closer to the top left corner. So model A does better than model B, which does better than model C. So the area under the curve is a mathematical measure of all the area, like these shaded areas, but also all this triangular area here. So this area here is 0.5, that's this triangle mathematically, and then anything beyond that 0.5 plus some amounts. So the ranges of the AUC are from 0 to 1, and 0.5 is this triangle, the straight line, which means a completely random a flip of the coin type of model. It's half of times it's right, half of times it's wrong, and anything that does better, uh, that is more outwards here, does better than that. Now, when you're comparing multiple models, the one with the highest AUC is the best one. And so that's the one that is closest to the top left corner. However, this is a very ideal situation on the left. On the right is a real data scenario. And there you can see that model A here does better than B and C. It's closer to the top left than both. But models B and C actually kind of overlap. So that means that for some kind of cases, model C does better. Other kinds, model B does better. But overall, which one does better? Well, that's why mathematically there's a need to calculate the number, area under the curve. I'm really not a fan of single measures for classification evaluation. Usually, you need more than one measure to see different aspects of it. But one notable exception is the AUC. Uh, the advantage that the AUC has over other single measure scores is that it does not assume any given threshold. What I mean by that is that the measures such as sensitivity and specificity, even precision and recall, and for sure accuracy, assume there's a cutoff of what is determined to be positive or negative. That is predicted to be true or false, which is usually a 50-50 cutoff. But that doesn't always make sense because if managers want to be more conservative or more lenient, they might prefer an 80-20 cutoff or 70-30 cutoff. And there's no two managerial situations or application situations that are identical. And so a default 50-50 cutoff doesn't always make sense. And one thing that the AUC is very useful for is that it's at a point where the curve really begins, or like maybe here, or maybe around here or here for these curves, it tells where a manager could say that instead of a 50-50 cutoff of is true or false, you could say that if it's a 30% chance of being true, we'll call that true because we want to make sure we capture all the trues, or 20% chance of being false, then we'll call that false because we want to capture all the falses. So setting up where the cutoff is really depends on the managerial intuition. So if we look at the results that we have from our analysis in RapidMiner, so here, what the AUC curve is really doing, it's saying that how many times did the model guess correctly versus how many times did they guess wrong. And if the cutoff were set at what point, then how many times would it say yes? How many times would it say no? Right here, the cutoff is at 50 for yes or no. But if the cutoff were set at 40, then all of these would be yeses. If we're set at a smaller number, if we're set at 0.4, then all of these would be yeses, and so on. And the AUC is basically trying to figure out at what point, so whatever cutoff you are at indicates how many positives or negatives that you have. And that's the real value of the AUC. Not that it gives one number like, because 0.673 is actually not that bad, even though the actual accuracy, well, the recall is so bad, but the AUC of 0.673 is not that bad. The problem with this model is that it essentially set a cutoff at 0.05 to determine trues or falses, which is a default, but that's not a very good cutoff in this case. If the cutoff were set lower, then the numbers such as recall and so on would have performed much better. So the AUC is a much more useful holistic measure of showing the overall performance of the model that does not depend on the cutoff being 0.5 or 0.3 or whatever cutoff it is. And that's its managerial value. Now, there are tools in various languages. In RapidMiner, you can use operators, find threshold that finds what is the best cutoff that will give the best balance between true positives and true negatives, and can use the operators create threshold and apply threshold to set that. Instead of 0.5, you can set it at 0.4. Actually, I calculated with this data set, the best cutoff is more like 0.06. So with that, you'll have much better looking performance measures. And the AUC will remain the same regardless of your cutoff because it measures overall how well the model performs.